Hello students and welcome to lesson 7.06 dealing with oxidation and reduction. As always, we want to first mention quickly the standards that we will be addressing in this particular lesson. Here you see the main Common Core standards that we'll be looking at. If you'd like to read over those, you can pause the video at this time and read over them. You can also access them by going to Course Information and then selecting Standards. The objectives of the lesson is to first define oxidation and reduction, and then we're going to assign oxidation numbers to elements in a reaction, and then finally we're going to describe and explain what occurs during an oxidation reduction reaction. Now to do that, we do need to have some background knowledge, mainly from segment 1 or semester 1. The lessons are 3.05, 4.3, 4.4, and 4.5. In lesson 3.05, we deal with ionic charges and how we come about formulas in ionic compounds. And then 4.3 through 4.5, we deal with the different types of reactions. So make sure that you do go back over those and refresh on those if you need. We do want to have a good understanding of those lessons so that we have a successful experience with 7.06. So let's go ahead and get into the lesson here. First off, let's just talk really quickly about a real-life example of oxidation and reduction reaction occurring, and that is rusting. This is something that we all see happen all the time around us, and this is an example of what we call a redox reaction. That is short for reduction and oxidation. All right, and basically what's happening is oxygen is being oxidized, or excuse me, oxidizes the iron to form iron 3 oxide. All right. So what's happening is the iron is giving electrons to the oxygen, and they form this compound, iron 3 oxide. Now, of course, if you know anything about rust, you know that if you grab a hold of a piece of rust, it's very brittle, and it can flake off of cars and things like that very easily. Whereas iron, before it's rusted, is a very strong metal. So you can see how just by transferring and switching around, if you will, the electrons, we've completely made a different compound with completely different properties. So oxidation and reduction reactions are an important aspect of life, and we do want to, understand them and see how they work. All right, so let's use this example up here where we have sodium and chlorine gas reacting together to produce sodium chloride. All right, we go back to lesson 305. We'll remember that sodium, when it's in the neutral state here, has a charge of 0, which means it is neutral. Chlorine, even though it's diatomic, is in its neutral state here because it's by itself. There's nothing else there. So it too is going to have a charge of 0. Now when it makes a compound, remember that we have a transfer of electrons. The sodium gives 1 electron to the chlorine, so the chlorine had a charge of -1, the sodium had a charge of +1. Because we have 1 and 1 for the ratio, there's no crisscross, so that's why we ended up with a formula of NaCl. So we have neutral sodium becoming a +1 charge. We have neutral chlorine becoming a -1 charge. So each of them had something going on with their electrons, right? One of them loses an electron, and the other one gains an electron. Well, when it loses an electron, we call that oxidation. In this example, the neutral sodium was oxidized because it gave up 1 electron to become a +1 charge. And remember, electrons are negatively charged, so that's why it ends up with a +1 charge. The reason that we came up with this term, we being scientists, is because metals, of course, will react with oxygen, and they do that by losing electrons to form the metal oxides. So they, originally assumed that these reactions just happened with oxygen, so we called it oxidation. Reduction is just the opposite, where we're going to gain electrons. In this case, the neutral chlorine was reduced because it gained an electron from the sodium and now has a negative charge. So in this case, we call it reduction because when it gains a negative electron, its overall charge is lowered or reduced. So that's where the terms come from. Now, important to know, in this reaction we had both, right? We had sodium being oxidized, chlorine being reduced. You have to have both together. You cannot have one substance being oxidized and nothing else happening. You always will have one being oxidized and one being reduced. We live in an electrically neutral world, so if there's going to be a loss of electrons someplace, there has to be a gain of an electron someplace else. So they do happen together. All right, now here we have a couple acronyms that we use to help us remember which one's which, because sometimes it can get confusing. You can use whichever one you like. Oil rig, if you look at the word oil, we can say oxidation is loss, and then guys, just remember it's electrons that we're talking about. Rig, reduction is gain. And again, we have to remember electrons. For that reason, I personally like the second one. Leo the lion says grr because it has the electrons in there for us. Leo, losing electrons, oxidation. Grr, gaining electrons, reduction. All right, but again, whichever one you would like to use to help you remember which one's which, that's perfectly acceptable. All right, now so far we've been talking about ionic situations, all right, ionic compounds. Well, we also have to look at covalent compounds. All right, in a covalent bond, of course, we do not have a transfer of electrons. We have a sharing of electrons. Now, those electrons are typically not shared evenly. All right, we talked about back in Module 3 that you can kind of think of bonding like a tug of war. Well, if you have one that's stronger than the other, then the electrons are going to get pulled over towards the atom that's stronger. It's not strong enough to completely take the electrons from the other atom, but strong enough to pull them over towards its side. All right, so how do we determine which one's stronger? Well, that's what we call electronegativity. And again, that's something you should learn back in semester 1 in module 3. Electronegativity, remember, is an atom's tendency to want electrons. So the higher the electronegativity, the more it wants the electrons, therefore it's going to be stronger in that tug of war. So we have to represent this uneven sharing. And the way we do it is real simple. The one that is more electronegative is going to be more negative within the bond, and the one that's less electronegative is going to be positive. So we do that by simply assigning what we call oxidation numbers. We give the more electronegative one the negative oxidation number, and we give the less electronegative one the positive oxidation number. Now it's important to know that oxidation numbers are not necessarily the charge of the ions, because again we're talking about covalent bonds here. It's just a label that we use to help distinguish which one is the more electronegative and which one is taking the electrons versus which one is giving up the electrons. I mentioned this idea of oxidation numbers. We then of course have to know how to assign oxidation numbers. So we have some rules here that we follow, and when we're doing that, and of course we'll practice this here in a moment. First off, all neutral elements are going to have an oxidation state of 0. All right, we talked about that a little bit ago when we were doing the ionic example. Remember that also includes your diatomics, and there's a list of them right here for you. We've got hydrogen, nitrogen, oxygen, and then group 17, fluorine, chlorine, bromine, and iodine. Oxygen will have an oxidation number of -2, except in peroxides, which it'll be -1. And right here is an example of the most common peroxide, hydrogen peroxide. Third, ions, either by themselves or in a compound, will use their charge. So in other words, if you have a sodium ion, we know it's +1. It's going to have an oxidation state of +1. All right, for covalent compounds, remember we talked a little bit about those just a moment ago. We're going to pretend like they're ionic compounds. We're going to give the more electronegative one the negative oxidation state, and then the lower electronegativity the positive oxidation state. So generally speaking, we're going to start in the upper or top right corner of the periodic table. That one will be the negative one, and then as we move away from that, it'll become the positive one. And you'll see this as we go through some examples. All right, rule 5, the algebraic sum of all the oxidation numbers must add up to the total charge of the compound or ion. So if you have a neutral compound, when you add up the oxidation states, that has to equal 0. If you're dealing with an ion, then you have to add up the oxidation states and make sure it equals the charge of that ion. All right, and then of course, as we've already mentioned, the element that gains electrons is reduced, and the element that loses electrons is oxidized. Now, since we were mentioning ion charges, I did want to put the screen up real quick and just do a quick refresher. Remember back in 305, group 1 elements, when they form an ion, will have a +1 charge. Group 2 will have a +2 charge. The transition metals, group 3 through 12, can have various ion charges. So remember, that's why we use the Roman numerals to distinguish if it's a +2 or a +3 and so on. Group 13 will be +3. Group 14 typically is +2, sometimes +4. And then on the right side of the table, we now go the other direction, because remember, these atoms want electrons. They have higher electronegativity, so they're going to take in those electrons and end up with negative charges. So nitrogen's group will be -3, oxygen's group is -2, fluorine's group is -1. And then remember, the noble gases already have an octet in their outer energy level. They have their 8 electrons. They're happy just the way they are, so they are neutral. They have no ion charge. All right. So let's kind of put this all together and try a few examples here. First, let's just look at some compounds, and actually a compound and an ion, and then we'll look at a full equation and determine what's oxidized, what's reduced. Okay, so the first one here we have KNO3. Well, potassium is in group 1, so that tells us that it has a +1 charge. So that's going to be its oxidation state, +1. And we usually write the oxidation states above the compounds just to kind of keep things in a orderly fashion. Remember, our second rule was oxygen is -2 unless it's a peroxide. Well, here it's definitely not a peroxide. It's in an ionic compound, so we know it's -2. But we have 3 oxygens here because of the subscript. So we have to do 3 times -2, and we have a total of -6. All right, now going back over here with the potassium, there's only 1 of them, so of course 1 times 1 is still 1. So we have +1 here. Now, remember, we have to make the algebraic sum equal the charge of the compound. Well, in this case, it's a neutral compound, so we have to equal 0. So if I have a +1 and a -5 or 6, if I add those together, I end up with -5, right? 1 minus 6, -5. So to make it 0, what I would have to do is put +5 in here. So now 1 plus 5 is 6. 6 minus 6 equals 0. Now there's only 1 nitrogen, so of course 5 divided by 1 is still 5. So the oxidation state of the nitrogen would be +5. All right, so let me just clarify a couple of things here. The bottom line, this is the oxidation states. All right, so the potassium has an oxidation state of +1. Nitrogen's plus 5, oxygen's minus 2. The top line is just the math that we do to figure out our oxidation states. All right, this is something that sometimes confuses folks when we're going through these problems. So just make sure you understand that the top line is simply the math to determine the oxidation states. The numbers right here above, those are the oxidation states. All right. Now over on this other one here, SO4 minus 2. Here we have an ion charge. So instead of our algebraic sum equaling 0, in this case our algebraic sum needs to equal minus 2. Alright, so again, oxygen, it's going to be minus 2. It's not a peroxide. We have 4 of them total, so 2 times 4 gives us negative 8. Alright, so you kind of use it like an algebra problem here. X minus 8 equals negative 2. And we'd solve for x. Well, that means we add 6 to both sides, right? Or add 8, excuse me, to both sides. So negative 2 plus 8, that would give us a positive 6. Okay, again, all I just did there is I just basically made this an algebra problem. And I said x minus 8 equals negative 2. And to solve for x, we would just add 8 on both sides, right? Add 8 there, add 8 over here, and of course, negative 2 plus 8 gives us 6. Now there's only one sulfur, so that means it keeps all of that positive 6. So the oxidation state would be plus 6 for the sulfur and minus 2 for the oxygen. All right, so that's how we find the oxidation numbers. Now let's look at it in an equation, in a reaction. Okay, we're going to go through each compound and assign oxidation numbers. So copper by itself, remember in its neutral state, is going to be 0 for an oxidation state. All right, now silver nitrate. Okay, again, our second rule, oxygen is minus 2. We start with that. There are 3 of them, so 2 times negative, or excuse me, 2 times negative 2 times 3 is negative 6 for our total there. Now silver, okay, got to remember our ion charges. That silver is always a plus 1. Okay, if you forgot that, you could do the reverse crisscross. Going back to module 3, remember to get AgNO3, I'm going to write it down here on the bottom. Ag, the ion, and then NO3 was the other ion. Well, we got to remember our polyatomics. NO3 has a minus 1 charge, so that means the Ag has to be plus 1 to cancel it out. Okay, so either way you want to remember it, the Ag is plus 1 for its ion charge, so that means its oxidation state is plus 1. Now there's only 1 in the formula, so it stays plus 1. Notice that I am not multiplying by the coefficient in front. I'm only multiplying by subscripts. Alright, so again, our algebraic sum here, I've got 1 minus 6 equals 0, and I need to figure out what goes in the middle there. Well, if I put a plus 5, 1 plus 5 is 6, 6 minus 6 equals 0. So the oxidation state on the nitrogen is plus 5. All right, now on the product side, okay, reversing our crisscross, okay, just like we did with the AgNO3, we have a 2 here, so that tells us that we had a plus 2 on the copper. All right, so that was the ion charge. That'll also be the oxidation state. There's only 1 copper, so it'll say plus 2. Oxygen is still minus 2. Okay, but now we've got 2 times 3. There's 6 oxygens here. So 6 times 2 actually will give us negative 12. All right, so to make that equal to 0, in the middle here, I'm going to need a positive 10. All right, 2 plus 10 is 12. Minus 12 gives us a 0. Now remember, this 2 distributes through everything in the parentheses, so I have 2 nitrogens. So 10 divided by 2 will give me positive 5 for the oxidation state on the nitrogen. And then the final one, silver, it's by itself, so that is going to be neutral, so it is 0. All right, now everything has its oxidation state. Now we have to figure out which one was gaining or losing electrons. Well, we determine that by figuring out which one changed oxidation state. So if we look at copper, copper starts out as 0 on the left and ends up as a positive 2 on the right. So that definitely changed oxidation state. Silver starts out positive 1 and ends up 0 on the product side. So that definitely changes oxidation state. Nitrogen goes from plus 5 to plus 5, so no change there. Oxygen goes from minus 2 to minus 2, no change there. So for copper to go from 0 to plus 2, it had to release or lose electrons. Since it lost electrons, that means that copper was oxidized. For the silver, it goes from plus 1 to 0. So it was reduced in oxidation state, and it did that by gaining an electron. If you take a positive 1 and you add a negative charge to it, then you now will end up back at 0. So the silver was reduced. All right, and that's it. That's how we do it. We assign oxidation states, figure out which one's changed. If they go up in oxidation state, it's oxidation. If they go down in oxidation state, it's reduction. All right, now the last thing in the lesson was dealing with agents. Okay, an oxidizing and reducing agent. An agent is simply a reactant that causes something to happen. So an oxidizing agent is the reactant that causes the other substance to be oxidized. So if you think about it, the oxidizing agent is also the reactant that was reduced. The reducing agent is going to be the reactant that causes something to be reduced. So the one that was oxidized is also going to be the reducing agent. So if you look down at the bottom example here, I have aluminum reacting with iodine to give us aluminum iodide. Okay, in the neutral set here, aluminum has an oxidation state of 0. Oxidation in the neutral set also has an oxidation state of 0. In the compound, aluminum was plus 3, iodine's minus 1. So the aluminum goes from 0 to plus 3, so it was oxidized. Iodine goes from 0 to minus 1, so it was reduced. So the aluminum caused the iodine to be reduced. Therefore, the aluminum is also the reducing agent. The iodine caused the aluminum to be oxidized. Therefore, it is the oxidizing agent. Now, an important note here, when you're doing agents, it's always the entire compound that's considered the agent, not just the element that's being oxidized or reduced. This particular example, they're one and the same, but that will not always be the case, as you'll see in the example that we'll do here in a moment. All right, so let's kind of put that all together and try this one here. Determine which element is oxidized and which is reduced, and then what is the oxidizing agent, and what is the reducing agent. So again, it all starts by assigning oxidation numbers. All right, so let's start with our first compound here, the KiO3. Again, potassium we know is in group 1, so that's going to be a positive 1. Oxygen is minus 2. There are 3 of them, so it's going to be minus 6 total. There's only 1 potassium, so that's positive 1. So to make this neutral, I would also need a positive 5. There's only 1 iodide, so he is going to keep all of that positive 5. So the oxidation states are positive 1 on the potassium. Sorry about that, my 1 got a little messy. Positive 5 on the iodide, and negative 2 on the oxygen. All right, now we try the same here with the H2SO3. Hydrogen will be plus 1. There are 2 of them, so it's going to be a total of plus 2. Oxygen is minus 2. There are 3 of those, so that'll give us a total of minus 6. So to make that neutral, I would need a positive 4, right? 2 plus 4 is 6. 6 minus 6 is 0. So that means the sulfur has an oxidation state of plus 4. All right, now the Ki. K, as we've already mentioned, is group 1, so it's got to be a plus 1 charge. Iodide is group 17, that's a minus 1. All right, plus 1 minus 1, that cancels out, so that one's easy. And now the H2SO4. Okay, so again, the hydrogen is plus 1. We have 2 of them, so it's going to be plus 2 total. Oxygen is minus 2. There are 4, so that's going to give us 2 times negative, or excuse me, negative 2 times 4, total of negative 8. To cancel everything out, I would have to have a plus 6, because it is neutral. So 2 plus 6 is 8. 8 minus 8 is 0. There's only 1 sulfur, so it keeps all of that positive 6 charge. All right, so now let's determine which ones change oxidation state. K goes from plus 1 to plus 1, so there's no change there. Iodide goes from plus 5 to minus 1. All right, so plus 5 to minus 1, it's going down the number line, if you will, so that means it is reduced. Okay, so we know iodine is reduced. All right, oxygen goes from minus 2 to minus 2, so there's no change there. Okay, hydrogen goes from plus 1 to plus 1, no change there. Sulfur goes from plus 4 to plus 6. All right, so that is going up the number line, if you will. So that is the one that's being oxidized, right? So sulfur is the one being oxidized. All right, so now for the agents. Okay, remember we said that the oxidizing agent is basically the one that's being reduced because it's causing the other one to be oxidized. But it's the entire reactant or compound that's doing that. So we would have to say then that not just I, but we would say KiO3 is the oxidizing agent. All right, and then the H2SO3 is a reducing agent. Okay, so again, the whole compound of that reactant is the agent, not just the single element. Very important point there. All right, so that is it for lesson 706. I hope that was a helpful experience for you. If you still need some more help, feel free to attend the tutoring sessions. Make sure you go through all the practice problems and examples in the 706 lesson. There is also a review sheet in the Resource Center. And once you feel comfortable with the material, feel free to go ahead and take the 7.06 quiz. Again, that can be found in the assessment or gradebook section of your course. I look forward to seeing you back here again soon.